All right. This is going to be a very different situation for all of us. I will try to end up doing things as best as I can to try to end up, not uh, uh, not putting you in a bad spot to the best degree I can. Uh, that obviously at this point you already know that we're going to be doing things through Georgia View, because otherwise you probably wouldn't have found this video. Um, and I'll tell you a little bit about how that will work. But before we do that, I'll give you a little bit of just a personal note on some of this. My own mother is 70 years old and is significantly immunocompromised. So that the fact that there are a lot of you all who are dealing with this sort of thing, I really do empathize with a lot. And I, you know, I will again try to end up working as best as I can to end up both doing what we have to do for the semester, but also trying to work with you, which is one of the reasons why the videos will end up being broken down into smaller chunks, which is why you're not going to end up getting, a 45, 50-minute continuous lecture the way that I otherwise would end up having a normal lecture period. Um, so in terms of the structure of the course, what we're going to try to do, and this is something where you need to communicate with me if there is a major problem. Uh, I will uh, I will end up putting together your regular exam on sapling learning. So I need you to end up checking to make sure that you, on whatever devices you have available now and will expect to have available then, if you have if you are able to end up getting on sapling, that's awesome. If there's a problem with you being able to get access with sapling, I really need to know this extremely early, so then we can end up trying to figure out something else we can do. But for right now, our exam, which is a little while out, but it's a couple of weeks out, um, that we'll end up working on how to deal with that. As far as when we'll have it, I will try to put up one of those doodle thingies to give you a chance to give me some different possible 2 hour time periods. So it can be whenever you're really looking to do that, as far as sometime when everybody can work together. So we will see how that will work. I don't mind doing it on a weekend, so it's not that it even has to be during a week. The final exam will be done at the scheduled time. That it is yea verily from upstairs that we will indeed do it in that time period. And I'd have to go back and look it up to figure out what time period that actually is. But our final exam will be as it was the time it was originally scheduled. Uh, so, as far as homework, we're still going to do homework on sapling as long as that will end up working with you all. I also will do an experiment with trying to have you all to scan in what would end up in the past being group quizzes. Even in the original syllabus, it doesn't say that they're all group quizzes. Most of them we have were group quizzes. These will end that I don't particularly mind if you end up being able to come up with some communication with other students with that. This is still part of the learning how to do it part. And speaking of that, that what I will do as far as office hours, quote unquote, go, that the regular office hours I've had, I still will end up maintaining. You'll end up needing to probably pop me an email. I'll be watching that like a hawk during the office hours, quote unquote. Uh, and if you don't remember what those were, my original office hours or Monday, Monday and Wednesday, from 9:30 to noon, and Tuesday, Thursday from Monday and Wednesday 10 to 12. Tuesday, Thursday 9:30 to 12, and on Wednesday from 10 to 11. On Friday 10 to 11. Excuse me. Like I said, it's a little flustered. So I also will end up being specifically for you all available on our regular old class time. So Tuesday, Thursday, 3:30 to 4:45. If you have, if you're wanting to end up talking with me, the easiest way to do it would end up sending me an email, and then I will try to set up so that we can do a video chat on Teams. If you have an issue with bandwidth on being able to do that, let me know, and we can do it sort of through text chat, or maybe you could scan in a problem that you're having, and then we can end up doing it text chat or whatever like that. So I will try to work with you as much as I can, but that's the best we can do with this situation. And I think that's most of the logistic stuff that goes into this. We also, as we move forward, so we're starting to get into actually almost physics stuff. We'll end up having a lot of things having to do with geometry. That's going to be, we've had some before, but some stuff with left and right hands and stuff like that that's going to be coming up in today's lecture period. And I need to end up talking about some geometry just in terms of how to interpret words that I use for geometry. One of the things that will be difficult on me is that the camera inverts the image, so that I'm having to end up doing a little bit of fuzzy business so whatever is to me going to the right is going to be to the left on the camera and stuff like that. So we'll try to make that as comprehensible as possible. So, and we have to do this because if I was standing in the front of the room and I point a direction or whatever, then everybody knows which direction that is. But I don't know if you've got a camera you're going to be using. If you're doing this on a monitor, you're seeing me there, whatever. So, in terms of directions in space, that this direction, whenever I say up, that in general we're not going to be doing a whole lot of things with gravity. Whenever we do deal with gravity, I'll end up saying sort of upward from the surface of the Earth or something like that, to end up making sure that you understand I'm not necessarily talking about whichever direction that is on your device, so but if I just say up, that is the direction I'm talking about. So down would be that way, and left, which is going to be that way, and right will be that way, which again is backwards to me, but we'll deal with that. So, and that if we talked about into your screen, that would end up corresponding to that direction, which is also backwards to me, and that out of the screen will be that way. So again, when we're talking about in 3 dimensions, we have to have some terminology so you understand what I'm talking about whenever I give these. Okay. So now we're going to transition from all that intro stuff, but things we had to do, to the stuff that's actually new material. Okay, so we're finishing up then what we were talking about with momentum and that sort of thing by introducing a topic that's not exactly momentum but naturally fits with momentum, and that's the concept of center of mass. So if you have a system which is a collection of stuff, and remember, when it's a collection of stuff, whatever things are inside the collection at the beginning are still inside the collection at the end. So we can't say, well, this piece, all of this is in the system, but I'll cut this off and only deal with this half of the system later. If it's your system before, it's got to be your system after, with that provision in mind. We want to end up being able to describe where an object is. Because we talked about that a little bit, but it was kind of vague and halfway. So in order to be able to do it in a more coherent way, we end up going back to combining, if you end up looking at the lecture notes with this, we'll end up combining together the forces that act on individual particles inside the system. So Newton's second law says the sum of the forces acting on it will equal its mass times its acceleration. And so in terms of the lecture notes, I have a subscript of I, and what all that means is if you put a subscript of 1, that's particle 1. The forces on 1 is equal to mass of 1 times the acceleration of 1. Force on 2 is the mass of 2, acceleration of 2, and so on. So that's just Newton's second law for each one of them. And what we want to then do is to use Newton's second law to sort of define what we mean by the acceleration of the whole system. And we sort of define it by saying if we take the total forces acting on the system, it will equal the mass of the system times the acceleration of the system, which gives us a definition, definition of what the acceleration of a system could mean. So if it's something that's a solid object that's staying together, it's not terribly ambiguous. So, if it's staying together and it moves in whichever direction, then the acceleration of the object will be whatever the acceleration of any point in that system is if you keep track of it. But in general, you would have things that have different pieces. So I got a piece over here, piece over there, piece over down there. And if we consider those things that were separated from each other, possibly, as a system, we have to come up with a way to coherently describe what that acceleration is. So to put that together, the mass of the system, I think, is pretty obvious because mass is a scalar. So if I want to talk about the mass of a collection of objects, I just add them up, right? The mass of the first plus the mass of the second, and so on. Excuse me. But the acceleration of the system will define that way. And remember, of course, by combining Newton's second and third laws together, we can end up canceling out all of the individual forces acting in the internal part of it. So it's only the external forces that we have to worry about whenever we do that, which is one advantage doing this. Again, from what we talked about already with momentum before. So what we end up looking at to combine these together, if we end up expanding the right-hand side of that first equation I had, we get the sum of the masses times the change in velocity over change in time, and we're going to add all of those together for our system. And we're going to pick for this, for my acceleration to match, I got to have a short enough delta t so that it's pretty nearly a constant acceleration over that shorter period of time. And moreover, we're going to end up choosing a delta t that's small enough that will be small enough for all of the individual ones. So whatever the least delta t is that I can end up using for any of the particles in the system, that's going to be the one I pick. So then the sum of the masses times delta v over delta t for that will end up being, since we said equal, it will be the mass of the system times the change in velocity of the system divided by delta t, which now starts to give us a definition of what velocity of a system is. And the acceleration of the system we define the obvious way. Change in velocity over change in time if you've got a short enough change in time. So the last thing we're going to do is multiply that equation through by delta t on both sides. So when we do that, we can also then factor out the delta from mass 1 times velocity, delta v1 is delta of mass times velocity 1, because again, when we're talking about this, our system particles are the particles that stay together. So if we had a collision that broke apart, we're not the thing that broke apart. We're not talking about one object at the beginning. We're talking about all the little bits and pieces that there were at the end. Each one of those is one of our mass 1 or mass 2 or whatever. So by doing that, the mass of those things are staying the same. So I can factor the delta out of that, and then I can also then factor out the delta from the sum. So you end up getting what we've got in that next equation, the change in the sum of the momenta, basically mass times velocity, will equal the mass of the system times the change in velocity of the system for that teeny tiny little bit of time. But when I add this together over little bits of time, that all of those things collapse the same kind of way that they collapse when we were talking about momentum before. So we can end up saying that that will be true not only for a very, very short period of time, it will be true for a macroscopic time as well. And we will end up talking more about center of mass in the next video.